Everyone, welcome back to our mini-series on Möbius inversion. In this lecture, which is lecture 7, we're going to look at a beautiful question about visible points on integer lattice and the very famous constant that is 6 over pi squared. At the first sight, the picture on the screen is purely geometric, a grid of integer points and rays coming out of the origin. But hiding underneath, it is some surprisingly deep number theory. So our goal today is to connect three things: the geometry on the integer lattice, the Möbius function and the greatest common divisors, and the analytic side of number theory through the zeta function. Now, of course, we're going to talk about the 6 over pi squared. This magic constant appears in many different problems. We're going to look at the visible points and the relation with GCD of two integers. And we're going to say, what is the gcd-detector through the Möbius function mu. And we're going to calculate the Vn, which is the number of visible points within the range of, from 1 through n is the integer here. And we can look at what is called the density, which is the number of visible points over the total numbers. That will be the density. The density tends to go to 6 over pi squared as n goes to infinity. All right, let's go right into the lecture.
Last time we built the general Möbius inversion formula and used it to recover Euler's totient function from a simple divisor sum. The key trick was that the Möbius function cancels out contributions from non-trivial divisors.
I remember that we wrote a divisor sum for the identity function and then inverted it to solve for phi of n. So the same Möbius cancellation idea is going to help with greatest common divisors now?
Exactly. Today we will treat the condition greatest common divisor of a and b equals 1 as something that can be detected by Möbius. That lets us turn a geometric question, counting visible lattice points, into an arithmetic sum, and eventually into the constant 6 over pi squared. Inversion formula for arithmetic functions using mu of n. Recovered Euler's totient phi of n from divisor sums. Key pattern: 1 times mu equals epsilon cancels non-trivial divisors. Picture the integer grid in the first quadrant and stand at the origin. Draw rays from the origin to different lattice points. Some points are the first ones you hit along their ray, and others are blocked behind them. Lattice points are integer pairs, a and b, in the plane. The origin is at 0, 0, sending out rays in all directions. A point with coordinates a, b is visible if nothing lies between the origin and that point on the same line. It turns out this geometric idea is exactly the same as saying the greatest common divisor of a and b is 1. A point a and b is visible if no other lattice point lies between.
So v of n is just counting how many pairs a, b between 1 and n have greatest common divisor equal to 1. The visible points question is really a coprime pairs question.
Blocked lines of sight and primitive vectors. Think of each lattice point a, b as a vector from the origin. Points like 2a, 2b, and 3a, 3b lie on the same ray, just farther out, because they are integer multiples of the same direction. The vector from the origin to the point a, b points in some direction. If a and b share a common factor bigger than 1, then the point a, b is some integer multiple of a smaller integer pair. That means there is a nearer lattice point on the same line that blocks your view.
So the visible points are like the primitive directions, where you cannot factor out any common integer from a and b. That is exactly the greatest common divisor equals 1 condition.
It points in the same direction as the point ka, kb, for integers k greater than or equal to 1. MFBS detects when GCD equals 1. Here we encode the condition greatest common divisor of a and b equals 1 using an indicator function. It is 1 when a and b are coprime and 0 otherwise, and we express it as a sum over common divisors weighted by mu. This comes directly from the earlier identity that the sum of mu of d over all divisors d of n equals 1 when n is 1 and equals 0 otherwise. If we take n to be the greatest common divisor of a and b, that is exactly the sum over all common divisors. The indicator, 1, when the greatest common divisor of a and b equals 1, is 1 if they are coprime. Otherwise, it is 0.
So if the GCD is 1, the sum over its divisors is just mu of 1, which is 1. But if the GCD is bigger than 1, the different mu values add up to 0, making the indicator vanish.
The convolution identity is 1 times mu equals epsilon. Consider the sum over the common divisors, d of a and b. If the greatest common divisor of a and b equals 1, then only the term where d equals 1 remains. Checking the GCD detector on examples. Let us test the detector on the pair 6 and 10. Their greatest common divisor is 2, so the common divisors are 1 and 2. The sum of mu over those divisors is 1 plus minus 1, which is 0, matching the fact that they are not coprime. Example where a is 6 and b is 10, with the greatest common divisor of 6 and 10 equal to 2. For the pair 5 and 9, the greatest common divisor is 1, so the only common divisor is 1. The sum over common divisors is just mu of 1, which equals 1, telling us these numbers are coprime. The common divisors are 1 and 2, so we have contributions from mu of 1 and mu of 2.
So I can think of it like this. I look at the GCD of A and B, and then the Möbius values on its divisors either cancel to 0 or add up to 1 depending on whether that GCD is bigger than 1 or equal to 1.
Example where a is 5 and b is 9, with the greatest common divisor of 5 and 9 equal to 1. The common divisor is only 1, so we have a contribution from mu of 1. From the GCD detector to a formula for v. Now we turn the definition of v of n directly into a sum. It is simply the number of pairs a, b between 1 and n for which the GCD is 1. So we write a double sum over that indicator function. Next, we plug in the Möbius formula for the GCD indicator, introducing a third sum over d. Then we rearrange the order of summation so that we first fix d and then look at all pairs a, b that are divisible by that d. Start with a double sum over all pairs where 1 is greater than or equal to 1 and less than or equal to n. For a fixed d, the numbers between 1 and n that are multiples of d are exactly d, 2d, 3d, up to the largest one not exceeding n. There are floor of n over d such multiples in each coordinate, so we get a little grid of size floor of n over d squared.
So v of n is like a weighted sum over all possible common divisors d. For each d, we count how many points have that d dividing both coordinates, and then weight that count by mu of d.
Insert the GCD indicator written with mu of d. Now swap the order. First choose the common divisor d, and then consider the pairs a and b. The pairs where d divides a and d divides b are counted by the floor of n divided by d squared.
I think this is the essence of the lecture, where we understand the indicator here could be turned into this sum here. We add another sum of mu over the d factor here, right? So they are equivalent. And then since they're finite term, we're going to swap the order. You're going to have d here, and then this is when n goes to infinity, of course. And then here, the grid size is this floor square, right? So when you do the summation here, because it's over d, right? So the number of terms here over d. That's really important. Okay, that's kind of leads to the further conclusion that we derived. Make sure you understand this. The grid here is the floor of n over d squared. Now we give an example. If n equals 6, we have total n squared, which is 36 points. And when we consider d equal 2, we're going to have 6 divided by 2, which is 3 in one direction. In the other direction is also 3. So it's going to be 3 by 3, which is 9 points, right? So when d equal to 2, you get this 9. So that's the key steps in the formula.
geometric meaning of the floor term. To build some intuition, imagine zooming in on the points where both coordinates are divisible by a fixed d. You can factor out d and think of them as a scaled copy of a smaller grid. Fixed d, which means lattice points where d divides a and d divides b. After factoring out d, the new coordinates a prime and b prime run from 1 up to floor of n over d. So the points with that common divisor d really do form a little square grid whose side length is floor of n over d. Write a, b as d times a prime and b prime using integers a prime and b prime.
And then mu of d is telling us how to combine these smaller grids. Some get a positive sign, some a negative sign, and most cancel out when many common factors are present.
Normalizing the density of visible points. To talk about density, we divide v of n by n squared, the total number of lattice points in the square from 1 to n. This gives the fraction of points that are visible from the origin. Using our formula for v of n, each term in the sum picks up a factor that is floor of n over d divided by n squared. For fixed d and very large n, that ratio behaves more and more like 1 over d. Normalized by n squared, the fraction of visible points in the interval from 1 to n squared. Under suitable convergence conditions, we can justify moving the limit inside the sum. Then the density becomes an infinite series whose terms are mu of d divided by d squared.
So the geometric question, what fraction of points are visible, has been turned into the problem of evaluating a series with coefficients mu of d over d squared.
Rewrite using the v of n formula and divide both sides by n squared. For each d, the term is the factor of the floor of n divided by d divided by n, all squared. Link to zeta of s and the constant 6 over pi squared. From analytic number theory, we know that the Dirichlet series with coefficients mu of n is equal to the reciprocal of the Riemann zeta function when the real part of s is bigger than 1. Setting s equal to 2 gives exactly the series in mu of d over d squared that appears in our density formula. Using the famous identity that zeta of 2 equals pi squared over 6, we see that this series sums to 6 over pi squared. The Dirichlet series of mu of n is the reciprocal of zeta of s.
So the limiting fraction of visible lattice points in a large square is 6 over pi squared, and that is the same as the probability that two randomly chosen positive integers are coprime.
Plug in s equals 2 to match the series in mu of d divided by d squared. Recall that zeta of 2 equals pi squared over 6 from earlier work. Therefore, visible point density equals 6 over pi squared. Interpretation. Probability, two random integers are coprime. Summary. Geometry meets arithmetic. Let us recap the story. Visible lattice points are exactly the primitive vectors whose coordinates have greatest common divisor equal to 1. Möbius inversion let us rewrite the GCD equals 1 condition as a sum over common divisors with mu weights. Grouping points by their common divisor turned the counting of visible points into a sum involving floor of n over d squared. Finally, comparing our series with the Dirichlet series for mu and the value of zeta at 2 showed that the density of visible points and the probability that two integers are coprime is 6 over pi squared.
I like that a purely geometric picture of rays through a grid ends up using the same constants and functions that appear in analytic number theory.
A visible lattice point, a and b, is a primitive vector where the greatest common divisor of a and b is 1. Exit ticket, using the GCD detector. For practice, try to reconstruct the formula for v of n, starting from the idea that it counts pairs a, b with GCD equal to 1 and uses the Möbius GCD detector.
So I would start with a double sum over all a and b, between 1 and n of the GCD equals 1 indicator. Then replace that indicator by the sum over common divisors with mu of d, then swap the sums and count multiples of d.
Exactly. Doing those steps leads you to a sum over d of mu of d times floor of n over d squared, which is the formula shown here for v of n. The floor comes from counting how many multiples of d lie between 1 and n in each coordinate. For reflection, think about how this GCD detector idea might extend to more variables, such as counting coprime triples or primitive points in three-dimensional space, and what constants might appear there. Practice. Express v of n as a sum over d using mu of d and the floor of n divided by d.
Thank you for your time in watching this. Please like, share, and subscribe to the channel. Of course, we always would like to hear from you. Please make your comments below.